Welcome back. So let's start again, as we decided last week that we have 10 minutes of break. So we are just offset by 5 minutes. All right, so what are we going to do next? Now you know how to store data, right? I already asked you the question that I wanted to ask. So we've looked into relational databases. We made sure you learn SQL. Now you learn SQL, hopefully, and you know how to write SQL queries and query some small data sets. We've looked into scaling out, which means looking at clusters of machines on which you can spread the use of resources, be it storage, be it compute, and so on. So we've looked into scaling out. We've seen object storage. Object storage is this cloud service way of storing data in there in the cloud somewhere. And by now, you know that the cloud is not just up there in the sky, but these are actual machines that are stored in these data centers. They are right here on Earth. There are some in Zurich that are buildings that host all of that. They look totally like normal buildings, except that they consume as much electricity as in an airport. But apart from that, it's how it's done, right? So we saw that it's super simple. You have an object key, and you have the object itself. Right? We've seen that this is called the key value model. And of course, the object keys can be bucket plus object or count plus container plus blob, right? But it's still a key, all that together. All right, so now we can start storing data. That's the cool thing. So what kind of data do we store? Why do we store that data? So the first kind of data that you want to store is the data that you gathered from real life sensing, so to say. For example, you might have temperature sensors, you might have website logs that you're keeping, you might have events coming from, if you're lucky enough and you have access to the LHC and can throw a few protons at each other, then you might even have an event of all the collisions that happened there, some measurements and so on and so on. So then that's the raw data, and you can just already drop it somewhere. In some data lake, and S3 and blob storage are actually perfect for that. It's not the only way, but it's a great way of storing that sort of data. It's really the idea of dropping your data. You just drop it in there. There's so much space all over the planet anyway that you can store it, right? If it's not confidential, of course. Then what's going to happen is that you can also query that data. And when you query data, you basically produce more data. It's just that the data that you produce is then derived, right? So this is why I use the wheat and the flour here. But the idea is that you just aggregate or maybe do something with that, and then you have derived data, right? And what do? You store it again on S3, on blob storage, and so on, right? So we just keep creating more and more and more data by analyzing it. How do we analyze it? Well, I'm not telling you yet, because this is what we'll do in a few weeks, right? So for now, I'm just telling you how to store the data. But of course, in the future, we are going to transform this into this, right? So we are going to actually query the data. But what's important is to understand that we read from, for example, a cloud storage service like S3 or Azure Blob Storage, and we output the results of our query back to S3 or Blob Storage and so on, right? So this is what's important to understand. You read from a data lake and write back to a data lake. This is how the beautiful world of data lakes actually works. All right, but here's the thing. There's other solutions out there. There's big data and big data, as I like to put it. What we've looked into is actually a huge amount of large files. We can store billions or trillions of large files, not huge, just large. That's the 5 terabytes limit that I told you about, 200 terabytes for Asia. All right. So huge amounts of large files, but you're still stuck. You couldn't store as a single file this 300 petabyte data set of CERN, right? Why you want to do that is another question, but you can't. What about storing a large amount of huge files, right? What if instead I want the files to be bigger than 5 terabytes or 200 terabytes, much, much, much larger than that, more than a single machine? What fits on a machine? Can we do that? Well, the answer is yes, as we will see, and the technology that we use for that is the Hadoop distributed file system. As you noticed, we don't have a huge amount of huge files, because you can imagine the resources that a huge amount of huge files, like trillions of petabyte files, I can let you do the math, but we probably did not even produce that much data yet. So this is the reason why here I'm saying, okay, huge files, but then the amount is only large. All right. Okay. And what we mean is typically billions of terabyte files. That's the object storage use case, S3 and Amazon Web Storage, versus what we call now file storage, more like millions. We're not going to be in the billions of objects, just millions. But this time, the files can be much bigger than terabytes. They can actually be in the petabyte range or more. All right. So this is what we did last week and in the previous hour. This is what we do now. And again, I don't know why I actually put that slide again there, but yeah, maybe what I want to tell you is that what I told you you can do with S3 and blob storage, then you can also do it with Hadoop distributed file systems too. You can even read your data from S3 and output it to HDFS. So you can read from HDFS and output it to blob storage, right?
There's a question in the chat. What kind of files are this large?
Data sets can be this large. Data sets can be absolutely enormous. So with HDFS, you can actually store files that are this large. Right. I'm not sure if that answers your question. If you're satisfied with data sets.
Yes.
I think it's all over the news that there are gigantic amounts of data, right? We are probably by far now in the exabyte range at the scale of the mankind, probably even in zettabytes now. We probably arrived there. And yottabytes are arriving soon. We produce as much data in a few years as we've produced since the beginning of mankind, humankind. Just to give you this impression of exponential growth, right? So the data is really not what is scarce here. We have more than enough of it, and we have more than enough of it to have petabytes of data, right? And again, I'm not talking about data protection, privacy, and so on. Privacy is very important. Data protection is very, very important. Here, we are just talking about technology, right? Then how you use the technology, that's another aspect. Of course, there's laws that you need to comply with, right?
So the student said, but that sounds like a huge amount of small files, like pictures or videos.
Yeah, so pictures or videos would probably be small enough. Absolutely correct. We have another student who mentions the CERN data, and absolutely, the CERN data is an example of that. The CERN data is gigantic, the amount of data that is stored at CERN. So that's a good example. However, I must say, asking critically, do we really need that large files? Maybe you also mean as opposed to splitting them into smaller files. And that wouldn't be entirely incorrect. It's true that in practice, we actually do prefer to split into multiple files rather than have a huge files. So just because we are able to actually store petabytes of data doesn't mean that we actually want to have a single file that is 1 petabyte. But as you will see, the notion of blocks that we will see is still very, very useful, even if we are looking at files that are a few terabytes each. Right. Did I address your question? Again, it's very nice to ask critically and to wonder about these things. Yeah, all right. What I can add, thank you for mentioning the CERN data. So about the CERN data, how it works, it's actually very interesting because the CERN also works that way. Actually, they don't have just 2 levels, they have more than 2 levels at CERN. So there is basically the first level at which they just drop whatever comes from the collider, right? But in fact, they actually don't drop everything. They already start filtering back then. So they filter the obvious stuff, and that's already what actually ends up being stored is already a bit smaller than everything that is recorded. So there's already some pre-filtering. But basically, you have an initial data set that is absolutely gigantic. And what happens then is that they try to filter stuff very coarsely to extract a subset of that data that they think is of interest. And then they filter again and they filter again. So they basically, the data sets on which they actually work in the end are actually a bit smaller than the initial, much smaller than the initial data, right? They even produce data sets for schools for the purpose of teaching that are made in such a way that they arrange that there is enough interesting data or a density of interesting data to make it useful for teaching, right? But nevertheless, you do need that initial way of storing these enormous amounts of data in the first place before you filter out and reduce the size of the data set, right? So this also fits for CERN. All right, maybe some of you actually going, I don't know, maybe there are physicists who will be working with CERN later. There is an entire group interested in these things of how to use the querying technologies in order to query high energy physics data. All right. So what are we looking into now? We are going to change from billions of terabytes files where we looked into the key value model and object storage. Now we are going to a file system. So we'll have again this hierarchy of files and block storage that I'm going to tell you about. This is how we go now to potentially millions of petabyte file in theory, because again, your comment is valid that just because you can doesn't mean you will. Okay, so this technology all started at Google with the Google file system, GFS. The idea was that they needed a storage system that scales and that is also resilient, because if you have one single machine on your computer, it might fail once in a while. But if you have a data center with 1,000 nodes or 10,000 nodes, they will fail. In fact, there are people paid for spending their entire days replacing parts. When you're in a data center, you just keep going to change a hard drive, to change a memory stick, and so on and so on. And people are just paid for that to do that the entire day, because failures just happen all the time. So you see, it's an entirely different way of reasoning when you are in a data center. You don't replace the parts of your laptop every day, right? But in a data center, they do replace them every day, or at least something every day. All right. So basically, in order to design that system that was known back then as GFS, they need a way to monitor the data, to detect errors if there is a failure in a hard drive and so on, to automatically recover, even giving time to replace the hard drive and so on, but it shouldn't actually make the system fail in between. So even temporarily, before the hard drive is replaced, it should still automatically continue to work and recover and be in the end like that. And that's exactly how it was invented. Now, how do you use that system? Well, you probably heard of this random access thing that I already told you about, the idea of reading your hard drive randomly, right? You can read anywhere on the drive and ask for a few bits here and there. But for querying data, that's not what we want. For querying data, what we actually like to do is scan the entire data set. We like to read sequentially everything. So this is why the GFS and the HDFS, as we will see, are actually optimized for that, for scanning the file and not for randomly accessing or randomly writing data. Append data at the end of a file to just add more data, like logging, is also something typically GFS and HDFS now support, even though it was added usually later. It wasn't in the first versions, right? Why do you want to append data? Again, because of sensors accumulating data, logs, intermediate data. Maybe you also create your data on the fly as it gets produced. So this is why you want to have that kind of support. Finally, what else you need is that hundreds of clients should be able to connect to that system, right? And typically, it's not going to be a storage service like S3 that is global for everybody in the world. Typically, you're going to have that for each company. One company is going to have a cluster of machines, and it's the employees of the company who access that cluster of machines, right? Do we have a question?
Yes. So just to confirm, also with object storage in S3, we may split the object into blocks. So we're also technically doing block storage, which is what we are covering now from HDFS.
In S3, there are no blocks. That's the important part. In S3, you just have this black box. An object is a black box. You might have what resembles blocks in the way you upload that object the first time. Maybe you're not going to upload that object as a single time that you drop the 5 terabytes. You will upload small fragments. That's how the API of S3 works. And then at the end, you say, okay, all of my fragments are here. Please now create my object, right? But this is only a detail of the way it's uploaded. S3 does not expose any blocks. It doesn't exist in the S3 data model. You can still read objects partially, which we'll see is useful for Spark, but there are no blocks in S3. That's the important part. In Azure Blob Storage, there are blocks, but again, this is because I said it's a bit hybrid with what we will do today. That's the reason why I didn't talk too much about Azure Blob Storage before. Right? Did I answer your question, or does somebody remain in your question? Something remain? All right. Maybe I can add something that might also have been partly your question. Maybe it's because what I said, that when you have a data set, it's common to split the data set into multiple objects, right? Maybe this is because I said that instead of having, let's say, 1 terabyte file, maybe you're going to have 10 100 gigabyte files, right? But these are not blocks. These are really 10 files, then 10 objects. Right? I hope that also helps. By the way, you probably noticed that now I use file and object a bit interchangeably. It's actually the same thing. It's just that object is the name for S3 and file is the name for what we do now in HDFS, but it's really the same thing. When we say file, we also usually imply the block storage, while when we say object, typically not. But again, in Azure Blob Storage, they kind of do hybrid between the two. All right. Any other questions? Anything? Before I move on, give you an opportunity to ask. All right, then I'll continue. Please continue to ask questions, right? It's very important to understand these things. All right, so now here's another thing. I told you about throughput and latency. You know, this idea that we have now a huge capacity of storage, but throughput evolved a bit less rapidly, and latency even worse, right? Well, in GFS, in HDFS, in terms of performance, we prioritize throughput. We don't want to lose time in latency. It means that if you look at an HDFS cluster that is normally functioning with people connected to it and so on, what's going to happen in these clusters is just scanning. Data is just flowing around and flowing around and flowing around and flowing around. So it's really what we call throughput bounds, right? So the data is just going through the network and being read and read and read and read and read. It's very read intensive, right? And what I mean with latency secondary is that we do not want to constantly be waiting to receive data, because the latency is that moment where you're not receiving yet. You're asking for the data, but you have to wait until the data starts arriving. We do not want in that system to be stopped by that having to wait for the data. That's what will happen with random access. If you use random access, you are going to be constantly waiting for the data to arrive. It's very inefficient. This is really secondary. What we want is throughput. We want data to massively flow around and being read, and queried all over the place, right? What we'll do in the weeks after that. So this is how it was designed, because they already had in mind the MapReduce and Spark that would be used to query the data. All right, so this is what I mean here. The top priority is throughput. We want data to flow around as much as possible and as fast as possible. All right. So this is back to what I told you last time, that the progress between capacity, throughput, and latency. And now this is why I put that slide back. GFS and HDFS are designed to parallelize. And you will see that this is why we have the blocks too. The blocks are actually a great way to parallelize. And that I'll keep talking about how great blocks can be used to parallelize. And finally, they also have this batch processing idea. And this has to do with what I said here. The secret, in order to have data flow around and not be constantly waiting for new data, we will see the secret resides in the size of the blocks. If you carefully pick the size of the block, then you are going to be good with that. This is called batch processing. It means that instead of constantly picking like one record and then the next record and then the next record, instead of doing that, you just process, let's say, 100,000 records at the same time. That's called a batch, and that's why it's called batch processing. You download in one shot 100,000 records, and then you process them together, right? Batch processing. But I'll keep repeating that because, again, parallelism and batch processing, I'll probably say these words several hundreds of times until the end of the lecture. So don't worry if it's not clear yet. I'm not done talking about parallelism and batch processing. You will hear more than enough of that in the entire lecture. All right. So what is Hadoop that you might have heard of with this yellow elephant? It's when it was open sourced. So GFS was the proprietary version at Google, and then Hadoop was the open source version that was then created at Yahoo by Doug Cutting and some other people. It was done in 2006, slightly later than GFS. And the idea is really that they open source and created an open source version of the same technologies that Google did before. So the first one that we look right now is the distributed file system, Hadoop HDFS, Hadoop distributed file system. MapReduce, there's also Hadoop MapReduce, but that we'll see in a couple of weeks. There is also a white column store called Hadoop HBase. H is for Hadoop as well. This is in 2 weeks that we look into that. But today it's just this one, the distributed file system. And just so that you understand, this is what it is at Google. So HDFS actually was called GFS at Google, the Google version. MapReduce, well, here it's just the Google MapReduce, and that's the Hadoop MapReduce, but it's still called MapReduce. And Bigtable is the Google HBase, right? So HBase is the Hadoop one. Bigtable is, that's such a cool name. That was the Google white column store, all right? But these are proprietary. These are not the ones we look into. The ones we look into in this lecture are the open source ones. So HDFS, Hadoop MapReduce, and HBase. All right, and you can see the progress that started already now 15 years ago, more than 15 years ago. Initially, we had a couple of hundreds of machines, right? But then it scaled up. Sorry, I should say out. I have to be careful when I speak. We scale out, not up. So we scale out to more and more and more machines. It is believed the last time we heard anything about that, we were almost at 100,000 and at 600 petabytes of data. And then I don't know much about what happened after that. Did we get stuck in there and then we no longer grew, or we started using multiple locations? Well, I know that there are projects out there at many companies like Google that have even newer technologies. I'll tell you a bit about that can store quadrillions of objects with millions of machines, but this is really not big data anymore. It's enormous or gigantic data, right? But I'll tell you a bit about that. But anyway, the last time I heard about the Hadoop clusters, it was 5 digits, slightly going in the 6-digit range. And again, I told you the reason for that is that then you start having problems with electricity and cooling in the data center. Right? It's very hard to have more than that many machines at the same place because of all the real world problems that it starts creating. All right, this was the introduction. This is why I didn't get technical yet into explaining HDFS. Do we have any questions on the high level before I start diving now into technical meat of the system? Any questions? All right, if there are no questions, I'll just proceed. And now you will see today we start getting technical and more in the coming weeks. I'm going to show you more and more details, and we are going to learn about how this is all built and the secrets of how this is all working. You will see it's wonderful engineering. So almost every week, I'm going to start with the logical model, which meaning the high-level way that the user sees, and then we'll look into the physical implementation. That's the part that's hidden from the user, right? So how is it logically in HDFS? Well, I already told you a bit. I told you that in object storage, what we saw previously, there's this key value model where you have the bucket ID and object ID here, then you have the object there. But in HDFS, we no longer have this flat key value model, right? It's all flat there. It's really a table with 2 columns. Now in HDFS, what we have is a file hierarchy that should be quite familiar to you because this is what you have on your laptop too. So it's a hierarchy with directories and files, right? So HDFS has out of the box a file hierarchy. This is not like in S3 where I said you can also have a hierarchy like that by having slashes in there, but it's a simulation. It's not real, right? In HDFS, we really have this hierarchy of directories and files natively. That's the first thing that changes with HDFS compared to S3. There's a second thing that changed, and again, that's not new. I already told you about that. Instead of having a single big black box that is limited to 5 terabytes, now we have these blocks that a file is made of. the important part is that these blocks are exposed to the user. The user sees them, right? They are really part of the logical model. So we have block 1, block 2, block 3, block 4, block 5, and so on and so on. What happens with the last block? Well, the last block might be a bit smaller, of course, because what are the odds that it's exactly the size of 8 blocks, right? So it's very likely the last one is going to be a bit smaller than the others, right? But all the others, they have exactly the same size. All right. I gave you a warning, I think, already before that we are going to have sometimes plenty of words to mean the same thing. So the first thing that's going to happen, the first time it's going to happen now, is that in HDFS, this is called the block this here. But in GFS, they didn't call it a block, they called it a chunk. You just have to get used to it. We will see, there's the word block, the word chunk. Later, we will see the word split, the word shard, the word partition. These all mean the same things, but you just need to kind of remember which technology uses what word, right? But this is always the same idea of this batch processing thing, right? We just partition the data, we shard the data, we split the data, we chunk the data. We love to use these words as verbs too in English, and this is how it works, right? So I just keep using the word block, but just be aware that if you look at GFS, you will see that they say chunk instead of blocks, right? If you Swiss German, you're probably used to it. You know how in Switzerland, we love to use different words depending on the city, like Zündhölzli at one place, maybe they say Allumette at some other places, I don't know. So it's you can consider it a bit similar to Swiss German dialects, that people use different words to mean the same thing depending on where they work. Right. All right. What's next? Next is that what that means. If I now summarize what we have this hierarchy of directories and files, and the files are stored as blocks, which are represented right here. So maybe this file right there has 5 blocks. This file has 3 blocks. And this one has 4 blocks, right? This is the logical level. I didn't say how it's physically implemented, but this is how it works, right? So you see how hopefully now the contrast with S3, how it's different from S3. All right. Now, why blocks? I keep repeating myself because I really want to insist on why blocks are so important for parallelism and batch processing. The first reason why we have blocks is that files can be bigger than a single drive. Can be bigger than 5 terabytes. You can even store a file that is 100 terabytes. As you can imagine, if you don't have blocks, there's no way you can store it so easy, right? So you really have to cut the files into smaller parts that you call blocks. So if you want to even achieve petabytes, you really need to split the files into blocks, right? And the second reason is that a block is actually quite easy to understand. It's like the slices of a cake, right? So you can explain that to anybody, the notion of block, right? Even babies play with blocks. So this is a really, really simple level of abstraction that you can use on the logical level. And we absolutely love simplicity in database systems, because simplicity is the key to scaling out, right? The simpler your system is, the easier it's going to be to scale to thousands of machines. So this is why blocks are actually so popular. And you will see that when we start querying the data in a few weeks with MapReduce and Spark, it will be even more obvious why blocks are actually such a wonderful invention, right? Another benefit of blocks, because as I told you, it doesn't fit on one machine, is that when you have on the logical level all of these blocks that the files are made of, here I just threw them all in there, you can very easily reorganize them and spread them on multiple machines in any way you want, by the way. Just put 15 in there, 15 in there, right? Just like you would put sand or water in multiple buckets very easily, right? So it's such a simple abstraction that is really straightforward to distribute these blocks over multiple machines. Right? That's the other reason. And now I would like to use a bit your thoughts or pick up your brain. What do you think is the right block size for GFS or HDFS? What do you think we should pick as the block size? Just to give you the order of magnitude, I already told you that in your local laptop, on your hard drive that I don't know if you're on your laptop, but right here, the blocks are typically 4 kilobytes large, right? So it's 4 kilobytes. This is what you have on your simple file system. This is all hidden from you. This is really the physical storage that is made that way, that 4,000 characters are stored. These are the chunks that you store. But I'm not telling you what goes in there because I want to ask you the question, what you think the appropriate block size is in HDFS. given what I told you before about the requirements and what we want to achieve for a block, right? So this is why now I'm going to ask you the question right here. And my question is, what is the ideal size? I give you several, oh, need to reload the page. I give you several orders of magnitudes. 32 kilobytes, that's an alternative to the 4 kilobytes, same order of magnitude as on the local file system. Or 128 megabytes, it's a good compromise between latency and throughput. Or 2 terabytes, because that fits on the local disk, right? So we have 1 block per machine. Or 512 petabytes, because that's big data. I saw a question in the Zoom chat. I'll also answer to that shortly. All right. And I love that. The majority is correct. It is indeed 128 megabytes. That is absolutely correct. It's basically not too small and not too big. Right? It's indeed meant as a compromise. 2 terabytes, that's too big. Right? You would have 1 block per machine. It's not flexible. That doesn't allow you to spread blocks over a cluster. 500 petabytes, it's impossible, doesn't fit on a machine. 32 kilobytes, that would be way too small. If you have such small blocks, you will keep your time waiting for the blocks stuck in latency. And I told you that this is not what we want. So the idea of 128 megabytes, that's the batch processing idea. We batch process into bigger chunks, bigger blocks, the data. So now let's go back to the slides. So this, please learn by heart the order of magnitude. It's very important. It's not always exactly 128, right? In some systems, they change it. I think Cloudera, for example, makes it 64 megabytes. I don't know if HDFS might not also have that. What's important is the order of magnitude, right? And you can configure it. But I promise to you, if you try to change that and turn it into 32 kilobytes, you're going to have very poor performance. It's going to be awful. And the same is if you try to make it much bigger. Right? So this is really the sweet spot. So learn, if you want to learn one, just learn this one, like 128 megabytes, learn this by heart. How many records are there in there? You're already looking at thousands or hundreds of thousands of records in there potentially, right? So this is the batch processing. You're really processing, like if you have people in there, you're processing your 100,000 people at the same time in a single block instead of one by one. Now I'm coming to the question, Wenxi, in the chat.
Yes. Do we have a logical abstraction for block for files on our laptop?
Yes. If you're a system administrator, for a user of a laptop like myself, I don't see them. I don't see the blocks, and I don't even care about the blocks. Right? All I see are the files in my navigator, right, where in Finder for macOS. However, somebody who actually deals with the hard drive and really needs to have more control about how it's written to and read from the hard drive. For example, let's say you're the implementer of PostgreSQL. So you need to implement PostgreSQL, and you need to write down to the local drive in an efficient way all your SQL tables. These people who implement PostgreSQL, they probably have access to the blocks. They see them. So for them, on the low level, they see some logical exposure of the blocks from the operating system that Windows or macOS or Linux gives them. So the answer is yes, there is a logical abstraction, but really just for the few people who really need to actually see them, and not for people like us who use it on the higher level. And yes, that's an excellent question. I agree. Did I answer it? All right, perfect. You're welcome. That's what I'm here for. I'm here to answer questions and make sure that I transfer as much knowledge to you as I can in 14 weeks. All right. So that was the logical level. It's easy, right? You have a hierarchy and you have blocks, 128 megabytes per block. These are just zeros and ones. So now let's dive into the physical architecture, what it looks like in our data center, where we have all these computers that we described last time. So the first thing is, how do we connect the machines? You know that we have these network cables. No Wi-Fi. I can tell you they don't use Wi-Fi in data centers. There's really actual network cables. It's much more reliable than Wi-Fi. There is a way that you can connect the machines randomly. That's called the peer-to-peer architecture. It was very popular actually even 20 years ago. I don't know if some of you heard of Napster and all these peer-to-peer networks that got created. Glutella, I think, is another one. That's called peer-to-peer. Some systems use that. But actually, in our case, in the case of many systems that we will see, they have a centralized architecture. What happens is that there is a central node right there, a primary node. There's many other names for that, but there is a primary node that has a particular responsibility. So this is why it's centralized. And all the other nodes communicate with the central node, right? So this is how HDFS is built. This is how GFS was built. We would see that many other systems in this course will use that centralized architecture. And the way it works in HDFS is like this. So now I just replace the computers with these more abstract pictures. There are names for that. The primary node right there, the central one, is called the name node. So you have to learn that by heart. You cannot invent it, right? So this is called the name node. And the secondary workers there that are connected to the central one are called the data nodes. Well, it's not a mystery, I'm not going to keep it a secret, that it's called data nodes because this is where the data is. This is where the blocks are, right, on the data nodes. And the job of this node right there is just to centralize stuff and do some administration. And of course, I'm going to explain how that all works, right? So again, just like you learned by heart the 128 megabytes, you need to know by heart name node, data node. You will also find it with capital N. In the middle, that's called camel case. That just because when it's implemented in Java, that's the name of the Java classes that we love to write with the camel case convention, right? But you will also find it like this with small n, big N. It's the same, right? All right. Technically, the name nodes and data nodes, these are actually processes, just like, I don't know, Word or Excel or whatever software you run on your machine. These are not the actual machines. But in practice, since we have exactly one of these processes per machine, we identify the process with the machine. So when I say name node, I both mean the machine and the process running on it, right? When I say data node, I both mean the machine that has the data node process and the process itself, right? It's just the piece of software that handles everything. All right, so we have the name node here and we have the data nodes there. All right, so now how do we store that? Well, you probably, yes, by now, sorry. All right, so we have a file. What do we do with that file? You guessed right, we split it, we chunk it, we partition it, we shard it, we block it. Block it doesn't work, right? But all the other ones you can use as verbs. So we divide it, that's another verb, into these 128 megabytes chunks or blocks or whatever you call them, blocks for HDFS. And what happens is that then we are going to, surprise, replicate the blocks. By default, 3 times. So this block right there, that's an example. This one is going to be replicated 3 times. It's called replica. We have 1 replica of the block right here on that machine, 1 replica of the block right there on that other machine, data node, and the 3rd replica on that other machine. 3 times by default. You can change it if you don't like it. You can make it 2, you can make it 5. If you're paranoid about using data, or if it's super important data, you can make it 10, but by default, it's 3. What is important is there is no such thing as a 1st, 2nd, and 3rd replica. They are just interchangeable. They are just 3 replicas and that's it, right? So this one, and this one. And of course, it's spread all over. If you look at the green one, oh, this one actually is there 4 times, right? So here it's over replicated. The black one, no, that's purple. Purple is there twice, so this is under replicated. So it means it needs to be replicated more. So you see how it basically works, right? We just need to ensure in the long term that everything is there 3 times. Right. Do we have any questions so far? So this is how basically the files end up being stored as blocks. on the data nodes. Right, I'll keep giving you more details. I still have more to come. I'm just diving slowly into it. All of that is concurrently accessed. As I said, this is for one company, typically this HDFS cluster, and then you have all the employees of the company. Maybe this is CERN, right? And CERN has this cluster, and then there's all the employees of CERN at ETH, EPFL, and over the world that access that cluster concurrently. They typically first start with the name node, but then they might also go to the name nodes in order to get the data. Right? It's all done in Java. I think I already mentioned that. So the Hadoop implementation uses primarily Java as the language. But you don't need to care about that because you will see there's plenty of ways to access it without even knowing Java. Right? You can use it on the command line. You can use it in other languages. So there's many ways, or via REST API even, right? So what I told you was actually useful last time. But I told you can use a terminal, a host language, REST API. This all works in there. But the implementation was done in Java. All right. What will I do next? Well, let's dive a bit into that. This is the overall architecture. Let's start here. Let's start with the name nodes. Let's see what there is inside in there. What do we have? So the name node is the central node. It's responsible for the system activity. What do we have? First, it has the entire hierarchy of files. It's only a few millions that fits on the machine. So it has the directories and file names in there, plus access control. Access controls means that Alice can access that file and Bob can access that other file and blah, blah, blah. This is access control. There's a few security things in there, but basically it's just the hierarchy of directories and files, but just their names. Second, for every file with a path here with slashes, we have a file, a mapping to the blocks, not the actual blocks because they are too big, just some identifiers of the blocks, like I'm using colors in there, right? So here we have the green and the blue blocks. So the green, yeah, green and blue. And here we have 4 blocks, here we have 1 block. So this is also on the name node. The mapping from the files to the blocks. So now you know how to reconstruct the file. You know which block to look for. And finally, we have the block locations. For every block, the name node knows where they are. For example, it knows that the green block can be found on this machine and on that machine. The orange block can be found on that machine. And by the way, it's under-replicated. They are all under-replicated, by the way. They should be 3 times. So it means the name node will have to fix that and make sure that they are replicated. All right. This is why I'm stopping for today by showing you what there is inside the name node, the hierarchy of directories and files, their names, the mapping from the files to the blocks, the IDs of the blocks. The actual blocks are in there. And so you need for each block ID, you maintain the locations so that you know exactly where to find them. Maybe I can answer also the question in the chat before we finish.
Yes, are replicates randomly stored on data nodes?
Not exactly. There is a strategy for storing replicates. And actually, I will tell you about that next week, how we decide where the replicas are stored. It's kind of random in the sense that you want to spread them a bit in a random way, but it's not entirely random because as we'll see, there's tricks to still make the system efficient when we look into other technologies later. So I'll spend a few minutes next week to explain to you where the replicas are going to be stored, and that's going to become very clear. All right. So I'd like to finish on that, and then I'll let you go to the Mensa, just checking that you are following. If you have any doubt or anything that is not clear, please ask us. So here it means what I see here is that the speed is just right. I shouldn't go too much faster to make sure that everybody keeps following, but this looks good. Everybody understood more than half. All right, there is a paper on HDFS that I encourage you to read. I also have partly written in the textbook also that lecture, but it's not done yet, but you can also use that as an additional support that just repeats what I said, basically. All right, so that's it. So thank you very much for attending today's lecture. I hope you enjoy your meal, and I'll see you next week. Enjoy the exercise sessions. Thank you, Wenshi, for moderating this lecture. Goodbye.